start. Our next speaker is Venkat Guruswami.
Thanks, Zev, and thanks to the organizers for the opportunity to speak here. It's a very interesting mix of mathematicians and CS people here, so great to do this talk. So this talk is going to be about some linear algebraic objects which came up in some computer science connection but seem to have some nice connections to these dimension expanders. So I'll explain all these things as we go along, and this is sort of putting together works I've been involved in a variety of co-authors in the past 3-4 years. So thanks to all of them. Okay, so let's get started. So just at a high level, the theme of this talk is probably something called linear algebraic pseudo-randomness, where you want to understand linear algebraic analogs of Boolean objects like expanders, extractors, and so on, but with the rank of subspaces playing the surrogate role of what the size of subsets would be. Okay, and there are many examples of these. The main things we will see in this talk are dimension expanders, subspace evasive sets, but there are also rank metric analog of codes, and so on. And for this audience, I could just say these are intrinsically interesting, but they also have some connections to other areas of mathematics and computer science. They come up in arithmetic complexity, in polynomial identity testing, in constructions of Ramsey graphs, and also have some nice coding theory applications, list decoding, and network coding, and so on. Okay, but the talk I'll focus mostly on the mathematical part, though I'll lead off the talk with where we started this investigation from. So the main focus is going to be on something which we call a subspace design. And actually there's nothing designy about this. It was just sort of not a great choice of name, but we did agonize quite a bit to see what we could call it, but this is what we came up with. And there is now some other notion of designs, but at least when we coined it, there was nothing. But but basically it's a collection of subspaces with some sort of nice pseudo-randomness property, which seems quite powerful and underlies many different things you want. So the way I've structured the talk is I'll tell you why we define these objects, and I'll of course then give the definition and what parameters you can achieve by random constructions, and then we'll look at some explicit constructions, how do you analyze them, and also applications to dimension expanders. And with respect to the theme of this workshop, really both the analysis of the subspace designs and why they come up both involve polynomial method in an integral way. Okay, so the original motivation of subspace design was to basically improve some results in algebraic list decoding. Okay, so in particular there are these very fundamental family of codes called the Reed-Solomon codes, which probably all of you have seen, but just a refresher, you have some begin of finite field, and you take your message, which you think of as a low degree polynomial of degree k minus 1, and you encode it by its values at n places, where n is going to be more than k. So you're basically oversampling this polynomial, which gives you redundancy. Okay, and obviously since two low degree polynomials cannot agree on too many places, the different code words corresponding to unequal polynomials f1 and f2 will be far away from each other, and therefore even if there are a bunch of errors, you can correct these things. And how many errors? So basically, any two code words will differ in at least n minus k plus 1 places. So even if you start from a code word and go up to half that distance, you can still come back to that code word. This is possible combinatorially, but there are also many efficient algorithms starting in the 60s, even before we had polynomial time as the proxy for efficiency, which solved this problem efficiently. Okay, so all this is very classical, but what we would like to do sometimes is correct more errors for various applications, and when you correct more errors, it's not hard to see that Reed-Solomon codes are in some sense the best. If you try to correct more errors, at some point you will have to output more than one answer. So what do you do? Well, in that case, you just say, okay, in such cases, give me all the answers. So the list decoding problem basically is you have some error correcting code, and when you get a noisy word, you want to correct it up to a large number of errors e, so you're not guaranteed a unique answer, but hopefully you're guaranteed a small enough number of answers, and the question would be to find that list. Okay? So the question is, how much does this buy you? Okay? And I'm going to go through the coding part relatively quickly. It's not so important for the talk. It just sets the motivation. So it turns out if you just do random coding, typical probabilistic method, it will allow you to correct in the list decoding sense a number of errors which is almost twice what Reed-Solomon codes can do in the unique decoding model. In particular, you can get to 1 minus epsilon times n minus k. Again, k was the number of symbols in the message, n was the number of symbols in the code word. Okay, so and n minus k by 2 is the best you could do without list decoding, and here you can do 2x that, with some trade-off. The closer you get to that bound, you have to output more answers in the worst case, and that's the story.
So
And
all the time you think about large alphabet?
no, yeah, so for this I'm thinking about large alphabet, exactly. So the alphabet is important, so if you stick with binary codes, you can't do something like this, that's impossible. In fact, you can't do n minus k by 2 either. So I'm really thinking of large alphabets here. Okay, yeah, thanks. And explicit constructions are also known, but you can do a similar result for random result for any alphabet. The explicit constructions don't look so good in the small alphabet case. But for large alphabets, we now have good codes which basically get you all the way up to the 2x number of errors, though they sort of fall short in some of the other parameters in terms of how many answers you might have to output in the worst case, the list size, other things. And basically, it is improving those parameters which led to the definition of subspace designs. Okay, so I'll try to present that in a sort of a particular case, which is maybe easiest to explain. Where they come up. So our goal was to do better than Reed-Solomon codes. So somehow we looked in places which are more structured Reed-Solomon codes. So one such family turns out to be this, which is you take Reed-Solomon codes, but Reed-Solomon codes already are long. The length of the code is at least, the field size is quite big, at least the length of the code. But now you make it even bigger. So what I'm going to do is I'll take a field. The polynomials will be over a big field, but I'll only evaluate it at points in a subfield. Okay, the two things in the red are the important things. Okay, this is still a valid Reed-Solomon code. Everything I said holds, but I sort of needlessly made my alphabet very big. Because now q needs to be at least n, and my alphabet is q to the m. And m you should think of as some integer parameter, small integer parameter, 10 or something like that. Okay, so why did I do this? And the reason we did this is that for this, Chopping, Xing and I showed that you can have an algorithm which if you take this code and you corrupt it up to a number of errors, which is this, s over s plus 1 times n minus k. In s you should think of as a growing integer parameter. As you make it bigger and bigger, you're approaching n minus k. Okay, and where does this s figure? If you want to correct so many errors, this algorithm will tell you that all the polynomials you need to output will be in some subspace. You don't have to bother to read all this exactly, but basically it's going to be in some structured subspace where, so this is a bunch of linear conditions, but basically once you know the first few coefficients of the polynomial, the next coefficient will always fall in the coset of the same space W. Okay, so there will be some W for which this will happen. Okay, so I'm going to put this out on the next slide again. So this is the guarantee. It's not so important the form, but the main thing is there is some subspace W in which basically all the coefficients kind of repeatedly have to fall. Okay, this is what the algorithm does. I'm not going to explain this algorithm, but in the theme of the workshop, I want to mention that really the proof of this uses the polynomial method, which is quite common in algebraic list decoding. But here I specifically want to give a shout out to Salil, who I think it was exactly at Harvard maybe 7 years back when he explained to me that you can do this polynomial method with a simpler choice of parameters with degree 1 only. And that, this was when he was working on his pseudo-randomness monograph, and it turns out that it not only simplifies, it's not just a simpler way to present things in a book, but it also has further ramifications, and this one is one of them. Okay, in particular, it turns out by that method, any message which will be close enough within that distance to what you receive will have to solve some functional equation like this, and turns out the solutions of that functional equation have this subspace structure. Yeah.
Can you just say a little bit more about this degree 1 variant?
So degree 1 variant was here you do multivariate polynomial interpolation in x, y1, y2 to ys. So this s will figure in number of variables you use in the interpolation. And the degree 1 variant is that you just do interpolation where the total degree in all the y's is 1. So you only have a term like a1x, y1 plus a2x, y2 plus asx, ys. You will not have terms like y1, y2 or y1 square and so on. Okay, that somehow makes the whole problem linear, and really it was pretty much nothing what I say today would have happened without that variant. So that was very influential observation. Okay, and anyway, so that was just to say that there is polynomial method already coming up here, but I won't say more about this. But it's not, once you realize that, it's pretty much not difficult. It's just you just have to see that you get this structure. Okay, so again you have this particular structure, and so again just to comment a little bit on this, basically what this says in words is that each coefficient of the any polynomial you need to output will be in the affine shift of the same low dimensional W. And again, this S figures in the dimension of W as well. Okay, there is a trade-off again. So again, let me pause here for a second. As you try to correct more errors, as you increase S, the number of errors in red there increases. But you're going to get more solutions. How many solutions? You will actually get these many solutions because for each coefficient, you're going to be in a dimension S minus 1 space. And so the total number of solutions is Q raised to the S minus 1 times K. Okay, which is better than the trivial number because remember each of these coefficients Fi come from the extension field of size Q to the M. So a priori there are Q to the Mk polynomials. I have done better than that, and again you should think of S as in the ballpark of M but a bit smaller than M. So I've done better than that, but it's still not great because unless S is 1, which is just good old unique decoding, I'm still getting a big list. I'm getting an exponential list. So that's what it is. But then what we said was, well, you have this nice structure, can you somehow exploit it? Okay, and that's where subspace designs come. Okay, and then this is the punchline slide for the motivation. So we have this sort of property that Fi belongs to the same W for all the coordinates. How are we going to reduce the list size? Suppose we pre-code these messages. So instead of allowing arbitrary degree K polynomials, I only allow polynomials where the ith coefficient belongs to a carefully chosen subspace Hi of Fq to the M. Okay, that's my idea. Okay, that's like the high level idea. What would you like from this collection of subspaces? So you can say that if you add these linear conditions, plus you have these linear conditions coming from that polynomial method, you can prove that the total dimension of solutions you have to output is exactly going to be the sum of the intersections of W intersect Hi. Okay, this is simple to see because each Fi should be in Hi and it should also be in W. The affine shifts don't matter.
So here you're taking max over W or something like that?
Yes, okay, that this definition will come in the next slide. So really what we would like to do is that what do I know about W? I don't know much because I'm at the mercy of the algorithm there. So it can be any S dimensional subspace. But my answer would be, my total dimension would be reduced to this. Instead of S times K, it will be really this quantity. So I would like to insist that this quantity is small for every S dimensional space. I'll give the definition in the next slide. But of course I can do that trivially by just taking Hi to be really tiny. Right? I can make it like one dimensional or something. But then my rate of the code will suffer. So I have to keep my Hi's more or less full dimensional so that I don't lose my information theoretic rate. So what we will think of is have some new parameter epsilon, think of as a small constant, and these Hi should have low codimension, like epsilon times n. Okay, and this is, and if you lost me a little bit in the connection, don't worry. Really, all I'm saying is there was a very good reason why we defined this object, but you can follow this definition and everything else I'm going to say even if the coding connection wasn't great. So what we want in subspace design is we're going to fix some vector space. We had the extension field Fq to the M, but for subspace designs it's only the vector space structure that matters. So I have the vector space Fq to the M, and we have some desired codimension. We have a collection of subspaces, each of codimension epsilon m is said to be two important parameters, S, L subspace design, if no matter which S dimensional subspace you take, the total intersection dimension is at most L. Okay, so and I'll tell you what the probabilistic method gives you to give you a feel of parameters. But another nice way to think about this is that this is a collection of subspaces such that any low dimensional subspace intersects very few of them. A priori that is implied by this, because the total intersection dimension is at most. If you want, you can more or less think about it. Okay, the application is actually important. For the coding application, it's not so important whether it is this weak the guarantee or the strong, but for dimension expansion, it's very important. It is this. But really, you can think about this collection of subspaces such that low dimensional thing will not intersect will not intersect too many of these. Question, yeah.
For the coding application, should we be thinking of S as like 1 over epsilon?
Yes.
Or?
So for the coding application, you really want to think of S as some 1 over epsilon, M as some 1 over epsilon square. So these will be large but constants. For the dimension expansion application, which I have not talked about, you really should think of S and M as growing. So somehow, but there we can make epsilon a little bit bigger. But it's also important for the coding application, epsilon is small. So slight differences in the parameter regimes of interest, but the fundamental object will be the same. And what would you like? Obviously, to make this interesting, you would like to keep S. You would like to have a large collection of subspaces, but keep L small. Okay, that's what you would like. Any questions? Any other questions?
Do we care how large is this capital M at all, or?
Yeah. So again, for the best coding applications, you want M to be really big, and I'll say you'll see the probabilistic construction. But for say the dimension expansion constructions, really M is just any growing number would be fine. So again, what is exactly required is different. But the most challenging is if you get a lot of subspaces and yet L is not much bigger than S. Okay. And and just quickly, so what is a probabilistic? When you're confronted with something like this, just to see what is possible, you give these subspaces at random, and then this is what you get. And you can pick quite a lot of subspaces. So assuming S is not too big, because obviously if W is everything, you can't do anything. So assuming S is not too big, you can pick quite a lot of subspaces, like exponentially many subspaces, codimension epsilon m, and the list size bound will be S over epsilon. And S over epsilon is roughly the right thing you should expect, because S is trivial, because I can just take W to be just contained in one of the first subspace. So then you will get S right then and there. And also because the codimension of HI is only epsilon m, you can actually make 1 over epsilon of the HIs intersect this as well. You can pick a W which intersects 1 over epsilon of these, because the HIs are very low codimension. So putting these two S plus 1 over epsilon is the best you can do, and you get S over epsilon. Okay. And actually, I don't know if this is the best trade-off possible or not. That might be a good combinatorial question as well. And it turns out, as Salil was saying, we will apply this with S to be about 1 over epsilon in the list decoding application, and that will bring down the overall dimension of the space to, instead of S times K, which was prohibitive, some constant depending only on 1 over epsilon. So now you have your entire solution space is contained in a constant dimensional subspace.
Don't you must have many of the subspaces that intersect by law. So you can put W contained in the intersection of all of them. So maybe S over epsilon is the best you can get.
Yeah, probably. Yeah, I would suspect this is the best possible. Yeah. So again for this decoding application, just to close the loop, just if you don't worry about it, just works out with some parameters that you've suddenly brought down. You have K subspaces where K is a growing number, but only a constant number of them can intersect this W, and so you're in good shape. Okay, so if you get it at that level, it's fine. But the point is, these are random constructions. So if you want explicit codes, again the challenge is, can you give me an explicit construction with these properties? So that's going to be the thing. Okay, so the thing you mainly need to remember is this notion, the subspace design definition. Okay, so you want a collection of subspaces such that any low dimensional subspace intersects few of them, and more technically the total intersection dimension is. Okay, and what we can do is, it turns out, we can more or less match the random construction. So in a paper with Swastik, we showed that for large fields, so you want m dimension subspaces sitting in Fq to the m. If Q is bigger than m, we can get a collection of quite a lot of subspaces, not as good as the random construction, but definitely adequate for purposes, which essentially matches this. At least it gets the intersection bound completely. Okay, so this almost matches the probabilistic construction for large fields. And if you want things over small fields, you can basically use extension fields and come down to the small field, but that will convert a subspace design upstairs to a weak subspace design. So that's unfortunate. But that's the best we can do for all fields. And it turns out, so I'll come to these. So I already mentioned one application of these subspace designs, but it turns out these subspace designs had other applications. They also give very good list decodable codes for list decoding in the rank metric, where your code words are matrices and errors are low rank distortions of matrices. And here list decoding was, not much was known, and these things enable us to get optimal redundancy codes. And it also leads to dimension expanders, a connection I at least hope to come to the end.
Venkat,
Yeah.
can Can you remind us what's the weak subspace design?
Okay, weak just means that the number of things which intersect W is small. But I don't care about the total thing. Of course, a weak one, if I put a multiplicative factor of S, it becomes a strong one.
So the difference is between S and S squared.
The difference between S and S squared, which is not so significant for the coding applications, but it completely destroys the dimension expansion application. So again, which context you apply in makes something more important than the other.
Maybe what was the deal of that?
So no, Dual-Lovett was something else. It was something called a subspace evasive set, which is a large collection of points, not a subspace, such that any low-dimensional subspace contains few of these points, which has a very different sort of geometric-like feel, because you could say that how many points can you pick on the grid so that no three are collinear. That's the geometric, and this somehow generalizes that to finite field settings, higher dimensional spaces. So I think I mentioned their work in some other slide, but okay, and then, so just last year we also got a construction which works over any field, just to give you one more trade-off. So the only problem with this construction with Swastik was the large field size. So now we have a construction which basically works over any field, but then it pays a penalty based on the field. So it pays a logarithmic penalty based on the field, which for large S is better than the S squared bound. Okay, so this uses some cyclotomic function beats. But what is an open question? So the following kind of question is open. Can you give me a collection of M over two-dimensional subspaces? So I set epsilon to be half, and I just want a growing collection for which the total intersection dimension only blows up by constant factor. So many constants have gone away. Really, the only thing is I want a growing collection. Okay, and my S should be, I should have added that, S should be sort of linear in M. If I can get this, then I'll get explicit dimension expanders over all these. I think at some point I should define these dimension expanders. I think I've said them a lot. Okay, so I'll maybe come back to this. Okay. Any questions?
So again, how does the open relate to what you know?
How does the open relate to what we know? So
we know S.
So we know S log M
S log M
or S square, but we don't know this. But the thing is that these things give you a whole lot of subspaces. I just want a growing collection.
Did you also know this when the Q is bigger than M?
Oh, and Q is bigger than M, we know this, of course. Yeah, so the key is over any field here. Yeah.
You know that the Wozenkopf ensemble does not work, or we don't know whether it works or not?
Sorry,
The Wozenkopf ensemble.
Oh, I don't know. Yeah, I didn't think about that specifically. Okay, maybe we can talk after.
So basically it's also open like for say F2 and the S equals some delta M or...
Yeah, so F, in that case, this is the best field.
So we know S
It'll
log
be M log M. Yeah.
Right.
Yeah.
So we know S log
And by the way, it does give you some connections to dimension expanders. It will give you that subspaces of dimension 1 over log M density will expand, but it won't. Okay, I should define these. When I come to that, I'll tell you. Okay, but this is a sort of a clean challenge which is open.
Okay, I guess you'll talk about the dimension expander at
Yes,
some
yeah.
point.
Hopefully. So, okay, now to the meat of the talk. Let's just go on. Okay, now I'll tell you about the construction. Really, it's a very classic use of polynomial methods, so I think it's nice to show. So I wanted, so basically I wanted this S2S over epsilon subspace design of this codimension. So too many parameters there, but really what I will show you is this construction. And then just some natural choice of parameters gives me what I want. So what does this construction say? There are going to be some more parameters. We've already seen Q, M, and S. So those guys you are intimately familiar with now. So two more parameters, R and T. And then, but I will get rid of one of them quickly. I'll get rid of R. So basically I'll give you subspaces of codimension RT. A lot of them, basically Q to the R by R. And then basically the main quantity here is this funny looking MS by RT. You can think of it. I'll put the precise thing just because it's not so bad, but that's what you. Okay, you get more used to this. So you'll see. But I'm going to simplify things already. I'll get rid of one parameter. I'll illustrate this with R equals 1. So I'll give you omega Q subspaces over FQ. And I won't show you the strong subspace design property. I'll show you the weak subspace design thing. And I'll also make my life easy. Instead of assuming q is bigger than m, I'll actually assume the characteristic of q is bigger. If q is bigger than m. Okay, and I might say something about how to get rid of this. With all these things, this is what I want to show. I want to show a weak subspace design with these parameters. R went away. So now I just have a collection of q subspaces of codimension t in fq to the m with this property. Okay, the only scary thing here is probably this quantity, but when you see the proof, it will become natural. Okay, anyone? Okay, let's warm up. Let's do the s equals 1 case. So I want s-dimensional subspaces to not intersect too many things in my collection. Suppose my subspaces are 1 dimensional. So what do I want? I want q subspaces of q to the m, and I will make, okay, so I should have said that I'll make my life even easier. I'll assume t is 1. T is 1, s is 1, so the denominator is 1. So I just have to prove 1 comma m minus 1 weak subspace design. So I want a collection of q subspaces such that any one-dimensional subspace intersects at most m minus 1. Okay, a one-dimensional subspace is of course just spanned by one non-zero vector. So I just have to think about one vector. And really the main thing is what are we going to think about the ambient space as? We'll think about the ambient space as degree m minus 1 polynomials over fq. Okay, that's the meaning I give to the ambient space. And now it's sort of clear. You want, basically what you want a collection of polynomials such that for any point, because what's the one-dimensional subspace? That's just spanned by a point. So you want a collection of polynomials, you want a collection of subspace of polynomials such that for any point is contained in very few of them. Okay. If you think about it for 5 minutes, this is a natural construction. So what you do is that you take each point and you define, and again another hint is that I want codimension 1 subspace. What's a natural codimension 1 subspace of polynomials? Well, give it a 0 somewhere. Okay, so take alpha in fq and define the polynomials to be those which have a root at alpha. So that's my q polynomials. Alright, that's my entire construction in this special case. And now it's pretty easy to see that if I take a dimension 1 subspace that is spanned by a non-zero polynomial p, and that polynomial belongs to at most m minus 1 of these h alphas because it has at most m minus 1 roots. Okay, let me repeat again, the subspaces are polynomials which vanish at a particular point. So you vary the point, you get different subspaces. If I take any non-zero polynomial, any one-dimensional subspace spanned by a non-zero polynomial, that's going to intersect at most m minus 1. End of story. Okay, so that's the simple case, and this is actually called the moment curve, and this was known in various guises in many works before. So there's nothing new here. Okay, so now let me do the case, still keep s equals 1, but now I want to have smaller subspaces, codimension t, but I want to gain in my intersection by a factor of t. Okay, so I want to have, instead of m minus 1 subspaces, I want m minus 1 by t, because s goes away. And now again, it's a natural, if you think about multiplicities and so on, which we have done in many contexts, that's going to be. I keep the same structure of the subspaces, but since I'm allowed more linear conditions, let me just insist that p vanishes at alpha with multiplicity. That's my condition. And again, this argument is the same. If you take a one-dimensional subspace given by a non-zero polynomial, it can belong to at most m minus 1 by t of these h alphas, because each time it belongs to this, it picks up t roots. Okay, that's it. Alright, so the s equals 1 case is pretty easy, and as I said, was kind of well known before. Okay, and the main punchline is that we have to now do the s greater than 1 case, but I've already told you the construction. So the construction is going to be the same. So I define my q subspaces to be those polynomials which have t roots at various points in the field. And now I'll prove that this has basically this sort of subspace design problem. Okay? Everyone?
So the subspaces are still codimension 1.
No, subspaces are codimension t. Yeah.
Oh,
Yeah.
right.
But there are q of them.
But there are q of them. Okay? And the proof will now use the polynomial method. That's sort of a nice new version of it. I mean, it's in the sense where polynomials come from. So we are going to, so again this is a high level bird's eye view of the proof, and then I'll go into a little more detail in the next slide. So I am given an arbitrary S-dimensional subspace W of degree m polynomials.
Venkat, can
Yeah.
you just tell us what we are proving?
Oh, we are going to prove, exactly. So we are going to prove that give me any S-dimensional subspace W. I will prove that W intersect H alpha will be non-trivial for at most these many alphas.
And W is a collection of polynomials.
Yes, W will be spanned by S polynomials.
Okay.
And I'll take an arbitrary basis of it and define some other polynomial. Okay, so I'll come to that one. But that's what we're trying to do. You give me an arbitrary S-dimensional subspace of degree m polynomials. I need to prove it will intersect H alpha on at most these many terms. Again, I'm only proving the weak part. So what we're going to do is we're going to associate, the proof goes by the polynomial method, where we associate a degree ms polynomial QW with W. Okay, I'll tell you how to do that in the next slide. And then we argue that if H alpha intersects W non-trivially, like the intersection isn't just 0, then this QW will pick up T minus S plus 1 zeros at alpha. And together, you should see why this implies this, because each time these alphas are distinct, so this is a non-zero degree MS polynomial, each time it picks up T minus S zeros, so it can intersect non-trivially at most. So these are two things.
Univariate polynomial.
Everything is univariate, yes. Yeah. And again, this is just fits in the previous slide. What did we do for the S equals 1 case? S-dimensional subspace W was spanned by a non-zero polynomial P. We took QW to be equal to P. That was our earlier proof. Okay. So now we have two polynomials P1 and P2 spanning a 2D subspace. What do we do? That's the okay. And again, here is the object. So the choice of the polynomial is just going to be the Wronskian. So if W is the span of S polynomials, I define QW to be the. So I don't know if Wronskian is the determinant or the matrix. I always get confused. Is minor the determinant or just the thing before you take determinants? But anyway, the polynomial is this determinant of this matrix or the Wronskian. I think the determinant is called the Wronskian, right? I'm not sure. Okay. So again, what's the Wronskian? Maybe if you haven't seen this, so you put an S by S matrix where the first row is the polynomials, the second row is the derivative of the polynomials, and so on and so forth. And they have first S minus 1 derivative. Okay.
By the way, I guess that matters so much. Just wonder if the polynomial you would let it. I guess you wanted the degree of this polynomial should be larger, right, than the.
Yes. So degree is going to go up by a factor of S. Right? And these derivatives you can take as formal derivatives. I made my characteristic big. So.
And this is independent of the basis?
This is independent of the basis.
So it's a function of W, not P1 PS.
Yeah. I mean the non-sync there.
Oh, the non-singularity.
Non-singularity, yeah.
Yes, I see. Okay.
It's up to. So it's a usual thing. You change the basis, you'll multiply by a scalar in FQ, but that doesn't matter. Non-zero scalar in FQ, that doesn't matter.
Right. So the polynomial is up to the scalar multiples is unique.
Yeah.
So the degree is a little bit smaller than even, right?
A little bit smaller, yeah, because these degrees are a bit smaller. Yeah.
Right.
So one thing I should say that I don't know how I missed putting it in the slide. Okay, the degree is easy to see. There are S polynomials, S by S, each of m minus 1, and as Noga says, you can even, this is m minus 1, this is m minus 2, and so on. So you can even say a little bit. That's easy, but why is it non-zero? Well, that's the basic property of a Wronskian. So if you have a collection of polynomials, they are linearly independent if and only if the Wronskian is non-zero as a polynomial. Okay, so this is like a very classic fact about Wronskians. So, I mean, that's not hard to prove, but I won't say more about that. So this is a non-zero polynomial of this degree. So that gives me the first thing I wanted. Very good. And now the second thing I need to say is that if W intersects H alpha non-trivially, then this guy picks up a lot of roots. Okay, and so what does it mean? What is W? W is the span of P1 to PS. Right? So what does it mean W intersects H alpha non-trivial? Let's just go back to the definition of H alpha. It means that there is some non-trivial combinations of the PIs which vanishes at alpha with multiplicity T. So I can do basically that very same linear combination of these columns, right, will have the property that basically all of these guys, if I take that very same linear combination and evaluate it at alpha, that's going to vanish. And that already should prove that this determinant itself vanishes at alpha because there's a linear combination of these columns which is 0. But further, I had t zeros at alpha, but I've only gone up to s. So it turns out you can differentiate this determinant addition t minus s times, everything works. Okay, just a calculation. So that's why you get these methods. But if you didn't see that, just see that at alpha this determinant is 0. Because there's a non-zero combination of pi's which vanishes at alpha along with its first t derivatives. And I've only gone up to s derivatives. Right? So that's it. That's the full proof. Okay, so this gives us this fact that for any t bigger than s, and s, any t is sandwiched between s and m, you get this property. You have to set parameters carefully to get what I said. Okay, removing 3 simplifications, they're not hard to get rid of. First thing is I wanted, so I said that in general I give you way more subspaces, q to the r by r. How do I get that? I do the same construction, but the roots I'll pick not in fq but in fq to the r. Now the codimension instead of t becomes r times t, because these points sit in an extension field. But that's all there is to it. Nothing else changes. The strong subspace design property is literally the same proof, you just do a more careful analysis. So you prove that if this W intersects H alpha not just non-trivially, but the intersection has dimension 2, then you somehow pick 2x more roots. So you pick a number of roots proportional to the dimension of the intersection. More careful analysis will give you that. And the last part is, how do you get rid of this characteristic assumption? This was, by the way, this characteristic assumption is important because otherwise this Wronskian linear independence criteria is not true. That requires the characteristic is large, at least as the way I stated it. I mean, there are extensions of that which work over any characteristic, but then you have to differentiate too many times and it breaks the construction. So how do you, but we can weaken that to just the field being large. And really the idea is to use a different construction where instead of saying the subspaces or polynomials with t roots at a point, you say that they have t structured roots. So basically they are going to be 0 at alpha and some points related to alpha. Specifically it's p of alpha is 0, and then you take some primitive element of fq and then just say you're also 0 at alpha gamma and an alpha to the gamma t minus 1. Okay, so.
But then you lose something, right?
So you lose something because the number of such things will now be not q but only q by t.
So
Because you want them to be disjoint and stuff. Yeah. Yes, question.
So your QW polynomial is again going to be the Wronskian?
The QW, very good. I wasn't going to say that, but I'll say it now. The QW will be something which we call the folded Wronskian, where the first row will be the same. The second row will be P1 of gamma x, P2 of gamma x, and so on. Each time you multiply the polynomial by gamma. And actually there is some connection to derivatives. There is something called Q derivatives, and this is apparently some instance of that, but I don't understand this.
So there are no derivatives.
No derivatives, yeah. No. So I should have, just P1x, this will be P1 of gamma x, P1 of gamma square x, P1 of gamma to the s minus 1x. That's, and we prove that that folded Wronskian is non-singular if and only if the matrices are linear. Okay, so not hard. Okay, so we are done with the meat of the talk. Any questions? Okay, now I've told the central attraction in honor of Avi, the dimension expanders. That's coming next.
So what if you try to do is like algebraic geometry codes instead of this thing to reduce the field size?
So actually that's sort of what this result I mentioned, I won't go back there with this S log m,
the log m.
using cyclotomic function fields, that's what we did. But somehow, it still plays this extra log m factor. But that's really what we do. And there somehow the derivative construction doesn't work so well, at least I don't know how to make it nice, but the folded one works. So this is something, by the way, comes up from, there are variants of Reed-Solomon codes which we call folded Reed-Solomon codes in this work with Atri Rudra, and these kind of come from that. Which is also peculiar because we came up with the subspace designs from applications in these algebraic codes, but then we also constructed them from basically similar ideas to these algebraic codes. But somehow it still seems that you need this link. There's no, seems to be a coincidence. Okay, so hopefully you at least got some flavor of how these subspace design looks. It's an algebraic construction analyzed with polynomial method. And the subspaces are basically, you think of them as sitting as ambient spaces polynomials. So you give them some structured roots and that defines the subspaces. And then using some variants of Wronskians, you prove the fact that they don't intersect too much with any low dimensional subspace. So finally for the dimension expanders, I think I have probably 10-15 minutes, good time to do it some justice. So these were defined maybe 12, 13 years ago by Avi and also another. This is a set of by Barak and Priya Soshpilka and Victorson. And I guess many of you. So anyway, I don't know. None of this is written up. So apparently, Avi mentioned this in a talk in 2004 at IPAM. I tried to find slides or video of the talk. I couldn't. And this is basically just coffee shop notes, I think. I don't think there's a writer. So you can ask the three of the authors on the history.
The Journal of Small World Coffee.
Small world coffee, yeah. But it's a nice definition. I like it. So what is the dimension expander? It's a very natural object. You fix a vector space over a field. It can be any field. In fact, a lot of people have worked on, complexes and so on. But I'm mostly interested in the finite field case. But it makes sense over any field. You want a collection of D linear maps from F to the N to the F to the M, such that the following happens. If we take any low dimensional subspace of F to the M, that expands under the union of all these maps. So you apply all these maps A1, A2 to AD, you get different subspaces. You take the sum of those subspaces, right? With the smallest subspace containing all of them, and that will be a little bit bigger than dimension of B. So note that I can just take A1 to be the identity map, and then I get dimension B right off the bat. So the point is I want to get a little bit more expansion. So maybe I want alpha to be 1.1. Okay, and this has got a strong parallel with vertex expanders. In vertex expanders, what do you say? You have a deregular graph, let's say, and you want every small enough subspace, small enough subset of vertices to expand by some non-trivial amount. Okay, so that's the property you would like, and this is basically just inspired by that. It's a linear algebra analog. And sort of borrowing from the graph theory connection, you could say D is the degree of the dimension expander and alpha is the expansion factor. Okay, so this is the definition. Okay, I have the definition again up here compactly. For any low dimensional subspace, you expand by this. Two crucial parameters are how big can you make B. You would like ideally B to be as large as you can, and you would like alpha to be as large as you can as well. And when confronted with something like this, well, you put these maps at random.
So can I just ask, you said this is analogous to standard expanders. Is it also a standard expanders a special case for any?
If the AIs are permutation matrices, if the AIs are permutation matrices, if you have a dimension expander, it is also an expander.
Okay.
But it's not strictly correct, right? Because you can't take any dimension expander and build a vertex expander out of it.
If it is permutation, if the AIs are permutation
then it's
matrices, then
equivalent.
it's a special case.
Yeah, and actually, in that case, it may be even equivalent or something. I'm not sure.
No, I
You
think
apply
because
to,
you only
apply
restrict
to
attention to
unit
special sets, to special subspaces that are spanned by the,
okay.
by the elementary basis.
Okay. So it may be even this may be even harder than that. So
Yeah.
oh, okay, that's interesting. Okay, but AI shouldn't be permutation matrices. So okay, so if you pick these AIs at random, you get so two interesting trade-offs you can ask is how big can you make B? You would like it to be a constant factor of n. Let's say n over 2, nice number. So then n over 2 things will expand by let's say factor 3/2 if you take say 10 maps. Okay, hopefully that's correct. I just threw it out. I'm sure there's enough slack here that it should be fine. Actually. But then you can also ask how big can the expansion be? Well, if you take D maps, the best you can hope for is of course expanding by factor of D, and you can get greedy and say I would like to expand by almost D, but then of course B better not be more than say n over D. So these are the two extremes, and then this is something we'll call lossless expansion. You don't lose anything. Every map gives you a bang for your buck. And sort of a broad challenge is again to construct these maps explicitly. So you want to give these matrices in polynomial time. And maybe just a very good, too many parameters, just avoid it. The good ballpark would be to just give constant degree expanders. D is some absolute constant for which some linear size subspaces expand by some constant factor more than 1. Okay, so that's qualitatively a non-trivial benchmark.
What you wrote there for
every field. Yeah. So I'll say what's known about these next.
What you wrote for random is independent of the size of the field for every field.
Yeah.
Every finite field. I don't know how to do it.
every
field also.
Yeah.
I see.
Every field.
Every field. Okay.
So you need something.
May not be true.
probabilistic.
It's not.
I only know it for every. I have analyzed it for every finite field, but apparently it works for any field. The field doesn't play a role in this.
The computation of the probability, you're not doing union value.
Yeah, if it works for any Q is 2 or big, it doesn't matter so much. There is so much. You get such high probability things. It doesn't matter. I think I should take a look at it.
Okay.
But yeah.
But I think it's also one of those things where you move to a larger field, it makes your life easier, like the rank increases.
Okay, and for infinite fields, you need some
You have
like
to
geometry
go,
or
then you say there exists.
yeah. So it's not counting. Right.
Yeah, I don't know how
The
to
set
do
of
that.
bad constructions is in some variety of
Right. Yeah. So you need some
dimensions.
I see. Okay, there are two broad approaches prior to our work, and I'll briefly touch upon them and then connect it to what I talked about. So first approach is basically draws on like expansion in the graph world. So it takes expanding Cayley graphs and this Kasdan property and constructs it. The second one is monotone. So I'll have a slide on each. So Avi basically, along with this proposal, also made a conjecture that if you take a Cayley graph with a generating set under which it is expanding, and then if you take any irreducible representation of that group, then basically having the so basically rho of S. So where the representation maps those generators, that will give you a collection of linear maps, and he conjectured that those should be a dimension expansion. Okay, and this was proved by Lubotsky-Zellmanov for characteristic 0, and they also observed that for finite characteristic, there are some blocks in this. I don't know too much about it, but there are some reasons, causes for pause, why this may not be true, at least in general. And I think this was also discovered around the same time by Aram Harrow in a quantum context, where he gave these maps which expand, again for characteristic 0. So the upshot of all this is that for characteristic 0 fields, you basically have at least this qualitative thing I said. Linear dimension subspaces expand by a factor more than 1. Okay, and they are nice and explicit. I think the degree can even be pretty small, p and so on. It's quite good. But this approach is not known to extend to positive characteristic, and in particular finite fields which are of our interest.
Sorry, so how many maps raw you have? I mean, for some groups, there is many.
Well, I guess it will depend on, it is basically the degree of the expander, right? So you just have rho S. Rho S is just applying rho to each of the elements in S. That gives you a collection of
Yes.
Okay, the graphs with constant generating set which are expanding. That's a two of
So I think, yeah, you can take 3. I think you can even get dimension expansion with 2. I don't know if it's there in that paper, but people have looked at it. So the other more combinatorial approach was put forth by Zev and Amir in where they said, well, we know and love vertex expansion, so let's try to reduce linear, dimension expansion to vertex expansion. Question.
Sorry, I still have a
Previous
question.
question.
The choice of group one doesn't matter at all. I mean, it's another conclusion. We've forgotten completely about the group, and it doesn't matter.
That's my context.
No, we need to
Yeah, I don't know, do they prove it in generality or for some group?
No, for
just need the representation of the appropriate dimension.
But I guess you need a group to have like the irreducible degree growth, so it will be interesting.
You need if you want you need n-dimensional representation.
Yeah, so the group will be restricted by this. It should have, its representation should have components of degree growing in it.
Got it.
So I think anything with that will do. So here they said, let's reduce dimension expansion to vertex expansion, and they made this observation that if you take a vertex expander, bipartite vertex expander, but now the maps from the left to right, somehow they are monotone. You can arrange the vertices in a way where each map just goes down, it's monotone. Then by basically taking the adjacency matrix of this, such adjacency of such a bipartite graph, that gives you a dimension expander. And using this framework, they also got these kinds of dimension expanders of logarithmic degree using some constructions in the cyclic group. And this connection was implicit there to monotone expanders. It was made explicit by Zev and Avi in a follow-up where they called it monotone expanders and also constructed using some zigzag-like ideas, iterative ideas, monotone expanders of as small degree as you want, but not a constant. So it could be log taken 100 times, but not a constant. And they also noted that, these monotone expanders are a really tricky beast because you can't even prove they exist by any natural probabilistic method. So there is no natural ensemble of these monotone
I'm sorry.
expanders.
Can you say again what are monotone?
Monotone expander would just be that, so if I have
a graph expander.
So you take a graph like this, and basically the maps. So if you take a D regular graph, you can think of the adjacency as D partial maps, or let's say D maps, and then basically, so you can decompose it into matchings, and each matching should go down.
No, it's not. It's not down. It's just that they don't cross.
They don't cross. So and it's also not a matching. I guess.
It's a partial function that doesn't cross.
So it's a very strong sort of topological restriction on how the maps, adjacency maps look like.
So there is a fixed order on the right and
Fixed order on the left.
and no map crosses on the left. Same order.
No, none of these D maps cross something, and the union of these D maps is the graph. Okay. Very structured object. Okay, but later Burgen and Yehuda showed that using some very complicated tools in SL2R that you can actually construct constant degree monotone expanders. And again, no existence proof other than this is known as far as I know. And then this is quite remarkable because now it gives me dimension expanders of n over 2 dimensional subspaces expand by some constant factor, and this works over every field. And not only that, this connection to monotone expanders actually gives you matrices with entries in 0, 1. So it's literally the same matrix, the same collection of matrices work for every field. Okay, so it's pretty impressive. But my personal critique of this approach is that somehow it seems to reduce this linear algebraic problem to a sort of very difficult combinatorial problem. I mean, expansion is hard enough, vertex expansion is hard enough. Now you want monotone vertex expansion. And also it seems, and I could be wrong here, but it seems it's such a difficult object that if you want to study things like the trade-off between the number of maps and the expansion factor, degree and expansion, maybe it's not fine enough to study that.
So this going from monotone expanders to dimension expanders, I thought you were losing logarithmic in the degree.
No, that was just, they constructed monotone expanders of log degree. And that's relatively, like a 2-page construction, it's not so bad. But if you want constant, the degree is preserved. Yeah, really, the translation is very simple. You just take each of the maps, you think of it as a sort of a 0, 1 matrix, and those maps give you the linear maps. So it's very good. Okay, so I have, maybe not enough time to give too many details. So our approach is basically to use subspace designs to construct dimension expanders, and this completely works in the linear algebra realm. I don't have to map to combinatorics. And now we have two approaches to do this. The first approach is basically to view these subspace designs differently. It was, and this was done with Michael Forbes, and then we have a sort of ongoing work where we use some connections to rank matrix codes. So I'll talk about the first approach first. And one thing is that these approaches can also give unbalanced dimension expanders, where the right hand, you actually expand into a smaller ambient space, which, is sort of technically interesting. But maybe just this slide will help to at least connect up the two problems.
Can you do the converse also, where taking dimension expander and get a design? That would be good for you.
Oh, that may be nice. Yeah, I haven't thought about that. Yeah.
Okay.
Yeah, actually. Okay, so I want to view subspace designs as something which contains rank. So what do I mean by that? So if I had these, again, long back we talked about these subspace designs given by these subspaces HI. Let's say each HI is the kernel of a linear map EI. EI shrinks m to epsilon m dimensions. Okay? And actually in our maps the EI is very nice. There was just evaluation of a polynomial at some points, so its derivatives at some points. Now by the rank nullity thing, we have the following thing. The dimension of the intersection is simply the rank deficiency, dimension deficiency between W and EIW. Okay? So if you think about this, if I say that typically this dimension was small, then it means that typically EIW does not shrink W much at all. So it basically preserves the dimension of W even though it is mapping to a smaller space. Alright? So in particular, you can define this following object. So in particular, the subspace designs give what is called a delta lossy rank condenser. So basically, it's a collection. What is such an object? It's a collection of maps E1 through some EM, such that for every S-dimensional W, the dimension of EIW shrinks by more than 1 minus delta for only few maps. And this is simply just an averaging. We said that the total dimension here was at most L. So the dimension, you can lose delta S dimension at most L over delta S times. So in particular, if we had a subspace design which had more than these many maps, at least one of the maps will preserve the dimension of W up to this 1 minus delta factor. Okay? It's completely syntactic. It's just an equivalent way to think about subspace designs. As a collection of maps which kind of mostly preserve the dimension of all low dimensional subspaces. Alright, so I think that's somewhat clear. And now with this, what Michael and I did is we can construct dimension expansion relatively easily with this view. So the idea is to basically expand into a bigger space and then kind of shrink. Okay, so it's a tensor and then condense approach. So first you go from Fn to F2n and then you come back to Fn. So the first step is very simple. You have twice the ambient space, so I can expand by a factor of 2 trivially by these two linear maps. So I have these two linear maps, I have expansion factor 2, everything is great, but it's trivial because my ambient space is 2x. And then I have this condensing object. So now I'll do a one-third lossy condenser, where delta is 1/3. I'll map back F2n to Fn using these subspace design. And if I take a subspace design which has this sort of property and has enough subspaces by the previous connection, I'll be done. Okay, you have to just check the parameter, that's not. So, and how many maps will you have? You have 2 maps here. Okay, and I should say, what's the dimension expander? Sorry. You basically compose these maps. You apply Ti followed by Ej. There are T1, T2, and then M of these maps. So in general, these 2M maps give you expansion because the first step expands by a factor of 2. And in the second step, at least one of these maps preserves the rank up to 2/3 factor. So 2 terms, 2/3, 4/3. Okay, just a simple choice of parameters. And again, if you just have an M will be a large enough constant, this will work out. Okay, so M just needs to be more than 3 times C, where C is the slack factor, so that everything will be a constant. Okay, and now, okay, great. So, but now we need subspace designs, but I gave you subspace designs over large fields. Okay, and then that's by just plugging this in, you get a simple construction of dimension expanders with good expansion for linear sizes from large fields. And you can also zoom in a little bit and see, okay, what's the trade-off between degree and expansion? So the first step, if you use alpha maps, that gives you expansion factor of alpha. Okay, and in the second step, maybe you lose a small factor like 1/3, but you still have expansion about proportional to alpha. But in the second step, you need another alpha maps to condense from alpha n to n. So the total degree will be like alpha square. So this gives you expansion square root of the degree. Okay. Okay. So I have maybe 1 or 2 minutes. Is that okay? Is that okay? So I'll just tell you the ongoing thing as well, which is also. So this is some ongoing work with my student Nicholas Resch and Xiaoping Xing, where we give another approach to dimension expanders. And this draws inspiration from 2 ingredients. The first ingredient is a work we had with Chris Umans and Salil Vadan about 10 years back, where we took some nice progress on algebraic list decodable codes and literally viewed those codes as some sort of graphs. And using the analysis of the list decoding, we proved that these have some excellent expansion properties. Okay, so we draw inspiration from that, and now we also say that we have these optimal list decodable codes in the rank metric from work with my former student Carol Wang and Xiaoping, and now we are going to try to say, well, now we have some nice list decoding results in the rank metric world, which kind of roughly correspond to linear algebra analog of codes, and can we use this framework to get some results here. Okay, so and that's what we are able to do. At least we already get some results, and hopefully we get some more. But I'll at least tell you one construction which works, which gives you dimension expanders. So one thing, when you go from rank to rank metric codes, so you have these Reed-Solomon codes. The way you jump to rank metric codes is basically to use linearized polynomials instead of low-degree polynomials. So there was this word Gabudel in codes here. And that's exactly what it does. So instead of low-degree polynomials, you use low-degree linearized polynomials. So what are linearized polynomials over Fq? The only powers will be powers of Q. So this is what we do. Once again, so we want D linear maps from Fq to the n to Fq to the n. And basically, we think of the left-hand side as polynomials of degree k, where these linearized polynomials of degree k, where these coefficients come from some sort of subspace design. It will turn out that's important. And now the linear maps themselves are going to be very simple. I want D linear maps. The ith linear map will simply evaluate this f at alpha I, where alpha 1 to alpha d span Fq to d. So if I want D linear maps, I basically just evaluate at a basis of Fq to d.
Yeah, but I just comment, it should be maps from Fq to the K to Fq.
No, this is Fq. Oh, okay, no, it is Fq to the n to this because I have k coefficients. Each of them lie in an n over k dimensional subspace. So the parameters are a bit tough to grasp. But high level, just think of linearized polynomials on the left. Evaluation is basically evaluating at some basis. That's the map. Okay, and then to prove the dimension expansion, we sort of take a contrapositive view. We say that if you give me a low dimensional space, how many f can be such that f of alpha I belongs to this low dimensional space for every alpha I? That's exactly the contrapositive view of dimension expansion, which also was key to this GUV work, and we are able to analyze that. Okay, and I didn't say where these coefficients come from. It turns out they need to come from some form of subspace design. I won't get into the details, but just mention a couple of things. If you had these very good subspace designs which matched what a probabilistic construction would give us in this context, here there's slightly different variant of subspace design, but if we had the optimal ones, we can even get lossless dimension expansion, okay, which is very nice. But unfortunately, we don't have that right now. But what we can do is get an explicit construction, which is a slight modification of the earlier ones, and we can at least get expansion proportional to the degree, again for largish fields. And we can also make the dimension expander unbalanced, as I said. Okay, so that's another way to do this. And even in this way, subspace designs play a critical role because the coefficients have to come from that. Okay, so that's all I have. So we have sort of an emergent theory of linear algebraic pseudo-randomness, and it seems the subspace design is sort of a good object which ties together many things. It started from list decoding, but it has some other connections to dimension expanders, rank metric codes, and so on. And there are many open questions, but I guess the most obvious one is get optimal subspace designs and dimension expanders over all fields. Okay, so thanks.
Any questions?
Can you say a bit more about the, so just trying to get my head around the capital M, the number of subspaces, right? So in the first application, the coding application didn't want.
You wanted that to grow?
You wanted that to grow. And the second one, it seemed really crucial that it was constant because that goes into...
No, it just has to be at least a constant.
But you instantiate it with a constant to get constant degree, right? Isn't that one of the factors in your degree of your dimension expander? You do EI composed with TJ, and so you...
Yeah. So there we had 2M maps. So as soon as your subspace design was more than 2M, you were home free. Because we said that the number of maps which can fail to shrink is at most something. So if your subspace design was bigger than that, you're good. So any sort of growing number would be fine.
I see.
Or even like big enough constant setting those parameters. But so in particular, the challenge I said earlier, give me M over 2-dimensional subspace design of growing size, but where the S only becomes order S, this would be good. But it's really important that the S only becomes order S. If it becomes S log M or something, then you will start needing like logarithmic maps to overcome that. So this does give certain things over small fields as well, but you will need to pay some logarithmic penalties.
Actually, I want to ask about the, not small field, but the infinite field. So if you want to define subspace designs over C, does your construction give some like large subspace of subspaces?
Yeah, I think the construction I showed you should work over any field because the Wronskian criteria, everything works. So in fact, you will get some uncountably many subspaces such that any low-dimensional subspace in particular intersects only finitely many of them and so on. So I think that's true, right? The same proof should work.
And there you don't even need so there you just have infinitely many alphas.
Yeah.
And you can choose.
You don't need any,
We can count the dimension of this variety of subspaces that you construct. You can quantify.
Oh, I see this way to quantify based on whether it's a full dimensional set.
If here you get Q to the D subspaces, then it's like you'd expect to get a D-dimensional variety of subspaces.